We won't crunch any numbers, right? How's that? So I'm going to count on you remembering kind of the three physical phases. Okay, matter can either be a solid, matter can be a liquid, matter can be a gas. I know plasma's in there somewhere, but we don't worry about that. So if matter is a gas, remember that gases have like, well, a few things about gases. I just love gases, actually. I get all kind of excited. I don't know if it's because it's the end of the semester or what, okay? But usually when I think about gases, I draw a little box here, okay? And then in my box, I have particles, okay? And then in those particles have a lot of motion, so I usually, make a big old arrow. And actually, we're going to talk about the pressure of a gas. And if you kind of draw this figure, you can almost see where those little blue gas particles are bouncing against the wall of that container. And that's what we call gas pressure. That's what gas pressure is. So a few things about that is it's compressible. So I could take that box and squeeze it down, right? I could take that box and make it larger, or make it kind of a weird shape, and those gas particles will find every crack and crevice because they have all that energy, all that motion. I just think that is so cool. We say gases have an indefinite density. Remember, density is a ratio of mass to volume. So if I can go ahead and compress it or make it larger, I'm screwing with the volume. I have the same mass. Okay, so densities are kind of what is the density, right? The densities, though, that matter is not compact very much, so they're pretty low compared to solids and liquids. Because they have so much motion, they actually, if you had, for instance, if I took my blue particles and I added now green particles, okay, so I have blue and green, I have a gas mixture, basically. Oh my gosh, try separating those into blue and green. They just won't do that, okay? Why? Because they're just running around. They form a homogeneous mixture. Okay, and I mentioned the pressure. We're going to talk about gas pressure, and that's actually kind of related to the gas particles banging on things, including the wall of the container they're in. So it's kind of cool because we talk about ideal gas law equation, which some of you guys may have heard about before. Ideal gases. The cool thing about gases is we really don't care about its identity to a certain extent. We don't care if it's nitrogen gas, oxygen gas, carbon dioxide gas, hydrogen gas, water gas. It all behaves similarly according to these four variables, and I just think that is so cool. So again, I'm going to draw my little box. Okay, I'll try to draw neater. Okay, this is my box that I'm going to put. I'll just put one kind of gas in here. Okay. If we want to fully describe that gas without saying its identity per se, okay, we would want to say what the pressure is, how much it's banging against the container, the temperature that it's running around at, the volume of the box, and the number of moles. Okay, this is a new variable. Okay, we use the variable N for moles, the number of moles of gas particles that are in there. That goes a long way to getting us down the road with what's the situation with that gas. So, pressure. Pressure is force per area, okay? So that kind of, you can almost see it if you go with the whole box and gas particles within a box. Okay, well, in this case, for instance, let's just say that these two have the same mass. Okay, let's just say they are mass M. Okay, so we have a certain amount, gravity's going to kick in, and we haven't studied gravity, but I bet you're okay with that. Okay, because they have the same mass, actually they have the same force, downward force. Okay, but do you guys buy this? Just by eyeballing it, can you see where this area down here, call this A1, is actually less than A2? Okay, so if pressure is equal to force, the force is the same, divided by area, okay, can you see where this smaller area here is going to have a greater pressure? Okay, so same force, more pressure. more P. So, so pressure is force divided by area. Well, what's force? Well, we can look at force, I think, a number of different ways, but I'm going to say Einstein. Newton said that force is equal to mass times acceleration. Units of force are newtons, okay? Newtons can actually be broken down into the metric system, kilogram meters per second squared. So again, we're not going to get much into it, but force is newtons, okay? So 1 unit of pressure is actually newtons per meter squared. And that is actually a unit called a Pascal. That's one way to describe pressure. Now, with all of that said, guess what? We aren't going to worry much about pascals. But that's one way to describe pressure. So the units we are going to worry about to describe pressure are here. You'll work a lot of homework problems that the pressure is in units of atmospheres. Okay. So this is a popular one. Millimeters of mercury, and I'll kind of tell you how do you get millimeters of mercury from pressure, okay? Those are very important. If you air up your tire and your tire says PSI, okay, the PSI comes from pounds per square inch. So now I circled atmospheres and millimeters of mercury. That equality, because we remember how we used to use equality statements as conversion factors, that's an important conversion factor. It's an exact relationship between atmospheres and millimeters of mercury. 1 atmosphere is exactly equal to 760 millimeters of mercury. All right. Sometimes your homework problems have the units of torr for pressure. Is that not weird or what? And actually, the torr and the millimeters of mercury have a 1-to-1 relationship. I think actually your lab that you guys are going to do a week from Thursday has the table you're going to use has units of torrs. So millimeters of mercury and torr are the same. But okay, and bars and pascals, I wouldn't worry about it. So this is kind of a cool thing. Actually, the pressure that liquid exerts, or these liquids are exerting, is directly proportional to the density of the liquid. This is all just colored water, probably, and the height, okay? So that's to say, even though these have weird shapes, they're like, really? Okay? As long as they are the same liquid, your height is going to be the same. Same density, same height. So whenever you, let's go ahead and start here on Wednesday? Right, yes. Okay, good. Well, we got a few slides under our belt.